Hi everyone. So we'll start with the session in some time, but I guess today you might have got the news, right, that for this current year of JEE and NEET we have exams a little bit delayed. Like we have the exams coming up in the month of July, like July 26th we have NEET, and 19th to 23rd, like that we have the JEE exams. So these guys anyway got a lot of time, so it depends on how the current batch of students will use it. Not sure if there will be like they're saying there will be an reduced syllabus or something for the next year, but we have to see, only when the final details will come out we'll be able to know. But possibly there can be some reduced syllabus for the 12th board exams. That also we have to wait and see. Anyway, so we'll start with the session, guys. Like we have been doing, right, what we will do is quickly take a look at what is it that we have. Hi Tara, Shivaranjani, okay, Pratiksha, yeah. So I guess good number of us are already here, so we'll get started with the session, guys. Venkateshwaran, Harsha, okay. So we'll start with the session. So like the way we have been doing, right, we'll just quickly take a look at what is it that we have covered so far. So in the last class, right, we were basically looking at these carbon resistors concept, and also we have started with the micro level analysis of the current. Mirza Sanya, hi. Pranav, Revati, okay, Sham, yeah, hi guys. So this is what we were doing in the last class. Like we have seen, how do we remember these carbon resistor color coding, and we have practiced quite a number of questions on that. And then we have talked about how the micro level aspects of current will be discussed. Like we talked about how the conductivity value or the resistivity value will be related to the micro level phenomena in terms of the electrons movement. So this is what broadly we have covered in the last class. Okay. So in the last class, because we were discussing the micro level analysis, and you know that we are midway through that. We were just short of answering some of the important questions related to the aspect of temperature dependency on resistance or resistivity of materials. So that we said we will be able to answer it based on the micro level analysis. Okay. So we'll take a look at the important formulae, guys, that we have covered in the last class. So what are the formulae that we have done in the last class? Jahanavi Nilambari, okay, hi. So in the last class, right, we were looking at the expression for the drift velocity. So drift velocity value of it, right, will be equal to minus E by m into tau, where small e represents what? The electron charge, capital E bar represents what? The electric field vector, m represents mass of electron, tau is what? Relaxation time. Okay, Laurel, okay, hi. So this is what is the drift velocity. Then we have the current expression. Current will be equal to what? N E A into drift velocity magnitude. This is the formula for current we saw. And after that we have talked about the relation between current density vector and the applied electric field. What is the relation we have? J bar is equal to sigma into E bar. The same expression can be also written as what? E bar is equal to rho into J bar. So these are the two alternative relations we have in terms of J bar and E bar. Okay. Then finally we came and stopped at this sigma formula. So sigma is what? Conductivity. It will be equal to N E square by M into tau. This is where we stopped. And of course rho will be equal to what? 1 by sigma. So thereby rho, if you want to write the formula for rho, rho will be equal to what? M by N E square into tau. This will be the formula for rho. So this is where we have stopped in the last class. Okay guys. Now what we'll do is starting from here, right, we will try and see how we can explain the observations of temperature dependency on the resistance or resistivity of the materials. Okay. So Keshavan, Gopi, yeah, hi. So these are the important formulae, guys. You know, we have to keep these things in mind, you know, so because these are important, especially in the microanalysis area, right? We do get straight questions straight on the formula. So if you're able to remember the formula, means we'll be able to answer all those questions. Okay. So what are the important formulae we have here? Drift velocity formula. We have the formula for the current relation to drift velocity. And we have the relation between what? The current density vector and then electric field vector. And finally we have what? The expression for the sigma. What is sigma expression? N into E square by M into tau. Moving on, right, this is where we were looking the answers for, like, you know, we have already discussed in I think the first lecture itself, we discussed this point that the temperature dependency of resistivity will be for metals, right? What happens to resistivity? Resistivity value will be increasing with temperature. So we can see that what is happening to the Jivanath. Okay, Amoga version. Hi. So I'm seeing you after a lot of time, I think, Amoga version. Okay. So what happens to the resistivity? It will be keep on increasing with temperature. Whereas in case of the semiconductors, right, we have exactly contradicting behavior. What is the situation in case of semiconductors? If we increase the temperature, means we see that resistivity value is what? Decreasing. And we actually wanted to know the reason for this. Why for the metals it is increasing with temperature and why for the semiconductors it is decreasing. And the reason for this will lie in these two terms. One is number density, because both in semiconductors as well as the metals, right, the charge carriers will be electrons. Of course there will be some small difference in case of semiconductors. We will learn about that in the respective chapter. But one thing that will be an important parameter is what? The number density. Okay. And the second term is the relaxation time. So these are the two aspects using which we will be able to find out the reason why metals we have a different behavior and then semiconductors we have a different behavior. Okay guys. Now before we go and look at the reasoning, right, let us just quickly try and understand what happens in these semiconductor materials. I mean, we'll talk about this in as much detail when we go to the semiconductors chapter, but let's just take a quick look at it. You know what happens in a semiconductor? Semiconductor, like if you take silicon, we'll have all the silicon atoms which will be what? Covalently bonded to each other. So in fact silicon, each silicon will be bonded to 4 more silicon atoms. It's a polymer kind of a structure. Okay, so each silicon is going to be bonded to 4 more silicons like that. Kavya, hi. So if you look at each of the silicon valency is what? 4. It has got 4 electrons. All the electrons will be tightly bonded to the neighboring silicon atoms. That's what it is going to be. Okay. Now if we look at, you know, where are these mobile electrons? Because what we said, for the current to happen we must have mobile electrons. Where are these mobile electrons? We see that each silicon is having what? 4 valence electrons and all of them are engaged in the covalent bonding. We don't see any mobile electrons for the silicon atoms. What happens is some of these covalent bonds will be broken. So thereby because of the thermal energy, the electrons in these covalent bonds, right, some of them will be able to come out. And when they come out, what they will be leaving behind is a gap. So one electron comes out means there will be a gap. Let us say here also the electron is coming out means there will be a gap. So in semiconductors we will be having electron and hole pairs. So what is a hole? The place from where the electron has come out, right? This is what we will be calling as a hole. Hole is basically an electron deficit site. What is a hole? Hole is an electron deficit site. Okay guys, so this is what we have in case of the semiconductors. Now here also the mobility is because of the movement of electrons only, but it is going to be because of both combination, electrons movement as well as holes movement. Holes will not move as such. Hole movement high ran. Okay, hole will not be moving because hole is nothing. It is a basically electron deficit site. What happens is the nearby electrons will come and occupy the site. Thereby the hole will be shifting to some other place. So in case of semiconductors, right, the current is because of the movement of electrons and holes. So the thing is, unlike metals, in case of metals, you know what happens? The number density is going to be fixed. It is not going to vary with temperature, because whatever the electrons in the valence shell or the outermost orbit, right, they will be mostly available for the conduction. So we will see that the number density will be fixed for the metals, but that will not be the case in case of semiconductors. Semiconductors, what happens is, if you increase the temperature, right, what happens? The thermal energy is going to be increasing. When thermal energy increases, more and more of these electrons, they will be able to get excited, they will be able to come out. So with increasing temperature, what happens is the number density part is going to increase. So what is the difference between semiconductors and the metals? In metals, the number density Karthikeyan high. So in metals, right, the number density will not be changing much with regard to temperature. But in semiconductors, if you increase temperature, means what happens? More and more of these covalent bonds can be broken. Thereby we will be able to have more number of mobile electrons. So with increasing temperature, right, the number density part will be increasing in case of the semiconductors. Clear guys? So this is what is the basic difference between the metals and then semiconductors. Semiconductors, right, we will again study in as much detail because we have one full chapter on them, like how these electrons and holes are going to contribute for the current. All of this we'll study in thorough detail, so no need to bother about it. Here we just need to understand the concept that the number density part will be fixed for the metals, and for semiconductors, increasing temperature is going to increase the number density. Okay, now we'll come to the important aspect where we need to look at the reasoning. So what is the observation we had in the case of the metals? Increasing temperature means resistivity is what increasing. We can also say it in another way. Increasing temperature, what we can say, conductivity is decreasing. Look at the conductivity formula. What is the conductivity formula? Sigma is equal to N E square by M into tau. This is the conductivity formula. Now for the metals, we said N is not going to be changing much with regard to temperature. E is anyway a constant. Janani, okay, high. So E is not going to be changing, and M is what? The mass of electron, which also will not change. Okay, Akash Vel, high. So E will be fixed, M also will be fixed, and the only thing that can change now is what? Tau. Tau is what? Relaxation time. Already we have talked about it. If we increase temperature, means what is going to happen? The collisions of electrons are going to be more and more. So when more collisions are there, means the relaxation time is going to what? Decrease. So as a result, increasing temperature is going to what? Simply reduce sigma value. Why it is reducing sigma value? Because relaxation time is going to decrease. So here in case of metals, right, the only thing that is getting affected because of temperature is what? Tau. Tau is decreasing when the relaxation time is decreasing, right? Why the relaxation time is decreasing? Understand this. If increase temperature, means the electrons will have more collisions now. Means between collision and collision, the time will be what? Reduced. So that is what we'll have as the effect of temperature. So tau decreasing means overall sigma will be what? Decreasing. So that's it. If you increase temperature, means sigma decreases. Sigma decreases means what? Resistivity part will be increasing. So this is what we have as Arvind, high. So this is what we have as the temperature dependency on the resistivity and conductivity for the metals. Now let us see the other side of it. What is the other side? Other side is the semiconductors. Okay. For the semiconductors, right, what is the observation we are having? Increasing temperature means, the observation is what? Increasing temperature means rho is decreasing. In other words, what we say, sigma is increasing. Conductivity part is increasing. So how do we explain this? Again, by using the formula of sigma. What is sigma formula? N E square by m into tau. Here also, increasing temperature means what? The electrons are going to have more number of collisions. So definitely increasing temperature is going to reduce the relaxation time. But as we have just discussed before, here increasing temperature is going to contribute for the increase of number density of electrons. And this is going to be more dominating. Like say for example, if tau is decreasing by some factor, the increase in number density is going to be many times more than this factor. So as a result, what happens? Let us say it is decreasing by a factor x, and this side it is increasing by a factor 2x or 3x. Overall, what is going to be the impact? Overall will be what? Sigma is going to increase. So what is the reason for this, guys? The increase in number density, right, or n, will compensate. It will basically compensate for the decrease of tau. In this case also the relaxation time part is going to decrease, but the increase in number density will be many-fold. So as a result of it, what is going to happen? What is going to happen, guys? We will see that the sigma in case of the semiconductors will be what? Increasing. So this is the reason for the difference in the behavior of metals and the semiconductors. Clear, guys? So what is the basic observation here? Metals, temperature increasing means what? Resistivity part will be increasing. Semiconductors, temperature increasing means what? Resistivity will be decreasing. Okay. So we'll look at this, guys. This is one of the important observations based on the microanalysis. Now the other property regarding this microanalysis is the term called as mobility. So mobility is something that we'll indicate with the symbol mu, and is defined as the drift velocity magnitude divided by the applied electric field value. So what is the way to measure the mobility? Mobility will be what? The velocity of the drift velocity magnitude divided by the applied electric field. So mobility will indicate, it's basically for these charge carriers, right? What is the ease of movement? That is what mobility will be indicating. In fact, this will be more beneficial if we talk about the electricity in case of ions, the electrolytes, right? There different type of ions will be having different type of mobility. But here we have anyway same kind of charge carriers which are electrons. So mobility is measured as what? Drift velocity magnitude divided by what? Applied electric field. So we already have a drift velocity formula, right? What is the drift velocity formula? E by m into tau. That is the drift velocity magnitude. We just have to substitute that. So what is it? Drift velocity magnitude by applied electric field, which is equal to what? This value divided by the applied electric field. The electric field will be cancelled. What we are going to get? E into tau by m. So what is the formula for the mobility? Mobility mu will be equal to what? E, basic charge, into tau, relaxation time, divided by m. So this is what is the idea of mobility. Okay. So we can have, not like we'll be, get a lot of questions on this segment, but any new physical quantity we have, right? There is always a scope for getting the questions on dimensional formula, and that is where we have to be careful, because sometimes, right, some physical quantities like this we will overlook. We'll talk about the drift velocity, we'll talk about the other things, but we might overlook things like this. And essentially when we go for the competitive examinations, right, we'll have questions from these kind of fringe areas sometimes. So we need to be ready to remember these physical quantities also. So let's look at one question, guys. What is the dimensional formula for mobility? So we understood what is the mobility and what is the definition of mobility. We need to find what is the dimensional formula for mobility. Let's see who can answer this, guys. We have to find what is the dimensional formula for mobility. Yes, guys, any answers? What is the dimensional formula for mobility? So how do we do? We have to look at the basic definition of mobility, right? How do we get the equation of mobility? What is the equation, guys, from where we can derive the dimensional formula? Look at it. Mu, mobility, is equal to what? Drift velocity by the applied electric field. We can use this formula. How do we measure it? Drift velocity divided by applied electric field. Okay, check it, guys. Anyone is able to get the answer? Rachel, Nidarshana, hi. Let's see, guys, if we are able to get the answer. What is the dimensional formula for mobility? What is the mobility formula? It is basically nothing but what? Drift velocity by the applied electric field, right? Any responses, guys? What will be the dimensional formula for mobility? Okay, Shanmugam, you got an answer. M power minus 1 T square A. Okay, let's see if there are more answers. Tasneem, M power minus 1 T square I. Okay, Mirja Sania, M power minus 1 T square A. Okay, so guys, I think some of us are able to already get the answer. So check it, guys. What must be the answer? M power minus 1. L power 0 means L will not have any dimensions. Then there will be T square and then either I power 1 or A power 1, because already we discussed, right? For the current, we can either use the symbol as what? Either I or A. Both of them we can use. The dimensional symbol for current can be what, guys? Either I or A. Okay, Jiva, Indu. Okay, so Aditya, Siddharth. Okay, so a lot of us are able to get the answer, guys. What is the dimensional formula for mobility? It's M power minus 1 L power 0 T square I or T square A. Clear, guys? And how do we find the dimensional formula? Mu will be equal to what? Drift velocity by the applied electric field. Okay, so I think you guys can do this question, but anyway I'll just give you the hint. Velocity is what? Drift velocity is nothing but velocity, L T power minus 1. Okay, electric field is what? Force by charge, means the charge will go to the numerator. So charge is what? I into T. Force is what? ML T power minus 2. Now that will give us the answer. This is going to give us the final answer. Okay, so that's the answer for this, guys. What is the answer? M power minus 1 T square I or T square A. Okay, okay, Amoga version, huh? Okay, sorry. Fine, so you got the answer correct anyway. So let's proceed, guys, to the next segment. So the next segment that we are getting into is this important area of electrical circuits in DC. The DC basically stands for what? Direct current. So in fact, in the entire chapter of this current electricity, right, especially this chapter, we are going to be talking about what? We'll be talking about the direct current. Okay, so what is this DC or who is this Prashant? So what is this DC or direct current? If you have current flowing in one direction, right, one particular direction, that is what we'll be calling as what? The direct current. And we'll have one more chapter in +2 which is called as what? Alternating current. Means in there the current is going to be changing the directions part. Okay, so we'll see, guys, what is this electrical circuits in DC. Basically, with regard to the electrical circuits in DC, right, we will be having components which will be a resistor. So these are the common components that we'll have, guys. There will be a resistor, and we already have some idea of what is a resistor. Okay, we'll see how we'll study more deep into this. Already we have talked about how the resistance value will be arrived at and all these things. Then later we will also learn about some more components like inductor, and in first chapter, right, we talk about a component called as a capacitor. So in the DC current circuits, right, we can have what? We can have a resistor, we can have an inductor, and we can also have what? Capacitor. So all these are possible components of the DC electrical circuit. But what is the driving force of the circuit? I mean, what drives the current in the circuit? The one that drives the current in circuit, right, is basically what we call as a cell or a combination of cells, which is known as what? Battery. So the driving force for the electrical circuits is what, guys? It is the cell or battery. Okay. So we will talk about the cell also in detail as we go into the discussion. But we'll have a cell which is typically an electrochemical cell. About this you will be learning in chemistry also. So there will be a chemical reaction happening inside the cell, and that is going to create a potential difference between the two electrodes. One will be at a high potential, one will be at a low potential. So the one higher we'll call it as a positive electrode, the one lesser we'll call it as what? Negative electrode. So to this, if we attach these components, I mean, we can have various combinations of attaching. Maybe we'll begin with what? Just resistors circuits, and then, you know, especially when it comes to little bit advanced level questions, right, not in the regular NEET level, but if you go to the JEE advanced level and all that, we'll also have the circuits where we'll have different components introduced, like we'll have circuits having inductor, capacitor also. We'll study about all these things as we go on, guys. But this is about the electrical circuits in DC. So what we'll have a driving cell or battery that will drive the current, and our conventional current will be what? The current that will start from the positive terminal, and it will come through these components, and finally it will be reaching what? Whatever the components we have, it will be reaching the negative terminal of the cell. So this is how we will be having the electrical circuits. And here the one important part of any electrical circuit will be that we have the connections intact, like the physical connections, right, is what going to be the key criteria for understanding of the electrical circuits, like how they are connected. I'll talk about what is the importance of that. The manner in which these electrical components are connected, right, that will be very crucial in analyzing of the electrical circuits. Okay. Now to begin with some very basic electrical circuit is you have a cell, which is this electrochemical cell. So this is what we were talking about. You have an electrochemical cell, and this cell will have two electrodes. One is the positive, other is the negative electrode. Okay. Or we can have the one with a high potential, we can call it as positive. The one with a low potential, we can call it as what? Negative. And what we see is that from the positive electrode, the current will begin, the conventional current, it will approach, and it will finally approach what? The negative electrode. So the current will be driven through the circuit by the cell or battery. And there are two things that we'll mainly analyze in these electrical circuits. One is what is the amount of current that we are drawing from the battery or the cell. And don't think too much about what is a battery now, because anyway we'll study more about what is a battery later. Battery is nothing but, for now we can think of it like what? A combination of cells. And the other part is how do we measure the potential differences between various points in the circuit. So these are the two main aspects that we will be analyzing with regard to any electrical circuit. And there is one more thing which is the aspect that will be important for the applications, that is the power calculations, because every electrical component, right, is nothing but what? It is going to be a part of a device, and every device is going to be consuming some power. So when it comes to the practical applications, right, we'll also be talking about what? The power calculations across different electrical components. So these are the three aspects that we'll study. Theoretically, right, we'll focus on these two. Practical applications will be involving what? They will involve the power calculations part. Okay, guys. So if you look at the representation of it, obviously, you know, in the diagrams we will not be having this entire representation, so we will not show the cell like this. We'll have a very simple representation of a cell like this. So we'll show the positive electrode with a longer line and the negative electrode with a shorter one, and from here, you know, the circuit, whatever the connections that are there, right, we'll be able to show, like, you know, here we have just one resistance, right, it will be coming over this. So this is what we will be having as a representation of the electrical circuit. And if you look at one of the important applications of an DC circuit, we said it is about the power dissipated, or the power that is spent in an electrical component. So if you have any electrical component, let us start with, say for example, resistance only. So we have a resistance whose value is what, R, and we are supplying some current I through that. So there is an I current that is flowing through it. So when current is flowing, it is nothing but movement of charge across this component, right? Let us say the potential drop is what V. So in some delta t time, if you observe how much charge would have moved, the amount of charge that would have moved, it will be equal to what, I into delta t, because charge is equal to what, current into time. Okay, so if we look at the work done in moving this charge, right, what will be the work done in moving the charge? The charge is moved through a potential difference of what, V. So work done will be equal to what, delta Q into V, which will be equal to what, I delta T into V. And this work is basically done by whom? It is done by the battery or the cell which is driving the current. And if you look at the work done by the time taken for this, we're obviously looking at what average values. Work done by time taken will be equal to what, I delta T into V divided by delta T. So this is going to give us what, I into V. So this I into V is nothing but what is the work done by time taken? This is the power. So to pump the current I across the resistor R, what is the power that is dissipated? It will be equal to what, I into V. And we can have alternative formula for this also, like if we have the current and resistance given to us, we can express V as what, these are alternative formula guys, V as what, V can be expressed as I into R. So I can have the power formula as what, let's say this is the first formula, I can have another formula. What will be other formula? I square into R. If we have say for example voltage and resistance given to us, from here, right, from the first one, I can have one more type of formula, which is I'll express I as what, V by R into V. So totally it will be what, V square by R. This is the third formula. So we can have either power formula as what, I into V, or we can have it as what, I square into R, or we can have it as V square by R. So we'll use whichever formula is required based upon the parameters given to us. Clear guys? So this is what is the idea of power dissipated across the resistor. Okay, and the power dissipation across a capacitor and other components, right, will have a different calculation. So for now we'll begin with just the resistor circuits. And if you have the entire circuit, so we can have not just one resistor, we can have like many resistors in different ways of arrangement. So across each component, right, we will see across each component there may be some power dissipation, and the overall power dissipation rate will be what is the power that is dissipated by the battery or the cell. So we add up all the power dissipation. Let us say here the power dissipated is what, P1, here it is P2, here it is P3. We add up all of them, right, that is going to be giving us what, the total power dissipated. So total power dissipated by the cell or battery is equal to what, sum of the powers dissipated across each component. Clear guys? So this is how we are going to be talking about the power dissipated in the electrical circuits. Now we'll see one sample question on this, but before we go there, right, there is one important aspect of every electrical device. Like, you know, if you see any electrical bulb, right, on the back side of it they would have given that, you know, it is 50 watt bulb, voltage 230 volt. So this notation, right, is what we call as power rating. So this is a very popular way of giving the power consumption of any electrical component, like, you know, a bulb or any, you know, tube light or any, I mean, you know, fan or any instrument, right, we'll give this power rating. So power rating will involve two things. It will involve one voltage and it will involve the power value. Now what is the significance of this power rating? The significance of this power rating is, if we apply this much voltage across that device, because remember guys, every device is what we can simply look at every device like a resistor. If you apply this much voltage across the resistor, it is going to consume this much power. So which means what? Power in terms of voltage and resistance, what is the formula we have? V square by R. So they are giving what? If you apply a particular voltage, what is the power consumed? Means whenever any power rating is given, right, one of the things that we can understand is what is the resistance value of that device, because the power rating will tell us what? If you apply this much potential, means how much power is going to be consumed. So straight away, if you use the power formula, right, what we are going to get from there, we'll be getting what is the resistance value of that particular electrical component. Clear guys? So whenever we have the power rating given to us, it is going to be helping us in finding what? The resistance value of the electrical component. Okay, so now we'll see one question on this guys. Look at this question. I'm sure you guys are able to read the question, but I'll just read out the question. An electric bulb is marked 100 watt 230 volt. So this is what I was talking about guys. Means what? It says if you apply 230 volts voltage, means the power consumed is what? 100 watt. That's the power rating of the device. Okay, now then statement of the question is this: if the supply voltage drops to 115 volt, the supply voltage means the voltage supplied to that electrical bulb is dropping to what? 115 volt. What is the heat and light energy produced by the bulb in 20 minutes? So we need to find what is the heat and light energy produced by the bulb in 20 minutes. Yes guys, we need to find out the answer for this. So what is given to us? They have given us the power rating. Okay, so from the power rating, right, we need to find what? We can find what is the resistance value. So from the power rating, we can find the resistance value. And for this electric bulb, we are using a supply of how much? 115 volt. And whatever the power consumed, right, or power dissipated, will be of course going in which form? It will be going in the form of heat and light. Whatever the power dissipated or whatever the power consumed, right, will be going in which form? It will be going in the form of heat and light. Okay, and we are not supposed to find the power here, we are supposed to find the energy, because time is given to us, right? Power into time will give us what? Energy spent. Look at this guys. What are the answers for this question? Anyone is able to get the answer? So first thing what we need to find guys, we need to find the resistance value. From the power rating we can find what? Resistance value. And using resistance value, right, if you are using this much amount of voltage, which is 115 volt, from here we can find what is the power consumed, and power consumed multiplied by time is what? The energy spent. And the energy will be going in which form? It will be going in the form of heat and light. That's what we need to find. Check it guys. Amoga version. Okay, I think today he seems to be on fire. Okay, so he's giving the answer. What is the answer he's giving guys? He's saying the answer is what? 30,000 joules. Okay, Kavya, you are saying B option, means what? 25,000. What about others guys? C option, Amoga version. Okay. Any other responses, guys? Shanmugam, C. Check it, guys. Others also. So I think Amoga version rarely goes wrong. So we must be having the answer as what? I guess we must be having it as what? 30,000, but we'll anyway check it. Okay. So first thing what we need to find, guys, from the power rating, right? We can find what? We can find the resistance. How do you find the resistance, guys? V square by P is what? Resistance. So 230 square by 100. That is going to give us resistance value as what? 529. This is the resistance value. And once we have the resistance, I mean, you don't need to do the simplification here. You can carry on and do the simplification in the final step also. But I mean, it's your choice basically. Okay. So once you have the resistance, right? Now we are not using a voltage of 230. We are using how much voltage? 115. So in this case, right? If you are using a voltage of 115 and spending it for a time of how much? 20 minutes. 20 minutes means how much time? In seconds, it is going to be what? 20 into 60 seconds. This much time. Okay. So the total work done by that the cell or battery or the source will be equal to what? V square by R into T, because we are talking only in terms of what? The voltage, resistance and the time. So work done is equal to what, guys? V square by R into time. So V square is what? 115 the square divided by R is what? 529 into time. SI unit is what? 20 into 60. So what is the answer, guys? Keshavan, Tasneem, yeah. Damodaran, Prajwal, you are getting answer D. Yeah? Check it guys once. So what must be the answer? It must be coming as what, guys? It will be coming as what? 30,000 joules. So what is the concept here, guys? We have been given the power rating. From power rating, what we can find? We can find what is the actual resistance value of the device. That we got it. And once we have the resistance, means you use it in some other voltage source. Accordingly, we will be able to find Akash Vel. Yeah, you also got the answer. What is the answer, guys? 30,000 joules. Use it in some other voltage means there we can find what is the work done by the source. So work done by the source will be equal to what? Power into time. Clear, guys? We will move on to the next topic. So one of the common ways of measuring the electrical energy that is consumed in the household applications is this unit called as 1 kilowatt hour. Okay, so this is not as such very important, but since we are discussing about it, right, maybe sometimes we may be randomly required to use it. So what is 1 kilowatt hour? 1 kilowatt hour basically means if you are using a power of 1 kilowatt and spending it for how much time? 1 hour, then what is the energy that is consumed here? So the energy value in terms of SI unit, right? 1 kilowatt means what? 10 power 3 watt into 1 hour. 1 hour means what? 3600 seconds. So that is going to be 3.6 into 10 to the power of 6 joules. So what is 1 kilowatt hour? It is an unit of electrical energy that is generally used for what? Domestic purpose and calculations like that. And what is the value in terms of joules? 1 kilowatt hour will be equal to what, guys? 3.6 in 10 power 6 joules. Clear? So we'll move on to the next important aspects, guys. This is what we'll slowly get into the electrical circuits. So if you have a cell and resistor, it's very simple aspect to study. So we have a resistor. We know what is the current that is drawn by the resistor. So current will be equal to what? V by R, because one cell is simply connected to the resistor or one battery is simply connected to the resistor. But normally speaking, in an electrical circuit, right, we will not have a single resistor. We may have multiple resistors and they will be serving some different purposes for us. So if you have combination of resistors, right, two simple combinations that we'll begin with are one what we call as this series combination, and there will be one more combination, we'll call it as what? Parallel combination. So here we are going to talk about what? The series combination of resistors and parallel combination of resistors. but the idea of what is series combination and what is parallel combination, right, is going to be same whatever electrical components we'll talk about. Like, you know, if we say series combination is connecting the resistors in this manner, then if you connect, say for example, capacitors in that manner, that is also going to be called as what? Series combination of capacitors. If you connect inductors in that manner, that is also going to be called as what? The series combination. So let us see what is the series combination of resistors. If you have resistors connected one to another in this way, where there will be no junction links, so between the resistor 1 and resistor 2, nothing is connected through the midpoint or the junction. And if you connect them like this, right, in case of resistors, what happens is, whatever the current that is going through resistor 1, same amount of current will be going through resistor 2. So since we don't have any junctions or branches that are in between, right, whatever the current that is going through resistor 1, same amount of current will be going through resistor 2. So this is what will be the significance of a series combination. So if you have series combination of resistors, right, each resistor is going to be having what? Same current flowing through them. Clear, guys? And if you have three resistors, right, let's say for example R1, R2, R3, do we have any junction connections here? Nothing is there. Means what? R1, R2 and R3 are basically what? They are in series. And we can see if I is the current going through R1, same current will go through R2 and same current will also go through what? R3. So this is what we'll call as what, guys? The series combination of resistors. If there is even one linkage like this, from here we are having one branch leaving or something like that, then this is not going to be called as series. So series means what? Between the two components we are connecting, there should be no intermediate junctions or links. Clear, guys? That is what we'll be calling as the series combination. And in case of resistors, right, if you have series combination of resistors, each of the resistors is going to be having what? Same current flowing through them. And in capacitors, right, the first chapter we will study that if you have series combination of capacitors, right, if you have series combination of capacitors, if this plate is plus Q, this is minus Q, this adjacent plate will be what? Plus Q, because both of them, they will take the charge from the wire only. This is taking minus charge, means this will take what? Plus charge. So if you have series combination of capacitors, right, in case of capacitors, all of them will be having same charge. That is what is the series combination of capacitors. But here we are not talking about the capacitors, we are discussing about what? Resistors. So series combination of resistors, all of them are going to be having what, guys? Same current. Now let us look at what is the parallel combination. If we look at every electrical component, right, we'll have two terminals. Let me mark it as what? 1 and 2. This side is 1, that side is 2. Here also 1 and 2. The terminals of the devices, right, or the components, they are connected across. Means 1 here is connected to 1 here, 2 here is connected to 2 here. As a result, what happens is the potential difference across the resistor 1, which is nothing but what? We can say V2 minus V1, will be equal to the potential difference across the resistor 2. So when we connect the things in parallel, right, what do you mean by connecting parallel? The terminals, because every component will have what? Two terminals. Terminal 1 and terminal 1 are connected. Terminal 2 will be what? Connected. So here the potential will be equal to here potential. Here potential is equal to here. So as a result, right, potential difference across both the components will be what, guys? Same. And that combination is what we call as the parallel combination. And usually what we see is if you are getting current to the junction of the parallel combination, right, the current is going to split. We'll see how the current is going to split. But what happens? The current is going to be splitting into the two branches. Okay. And again, as the parallel combination is closing, the current will again rejoin and then leave out. Similarly, if you have three resistors like this, we can see 1, 2, 1, 2, 1, 2. So the terminals of resistor 1, resistor 2, resistor 3 all are what? Connected across. Means when the terminals are connected across, that is what we will say. When the terminals are connected across each other, right, then they will be what? They will be forming the parallel combination. And when we have a parallel combination, right, across each of these resistors, what is going to be the common thing? Potential difference or potential drop is going to be same. That is what is the relation between the resistors in parallel. So and here also we can see whatever the current that is coming to junction, right, is going to be splitting into these three branches. We'll see in what ratio the current is going to be splitting also, but this is what we have as the parallel combination of the resistors. And we can have mixed, some of them in series, some of them in parallel, like that. Like if you see this particular representation, right, what we are observing, this R2 and R3 is what, they both are in parallel, and this entire segment is in series with R1. Like that we can have mixed combination of the series and parallel. And we'll see in this chapter that we may have the combination of resistors which will be neither parallel nor series also, but we are just beginning with what, very simple idea of series and parallel combination of the resistors. We'll see that there will be arrangements where the resistors are neither parallel nor series also. So the thing is, if we have a circuit where we may have a combination of resistors, here we are beginning with a very simple combination, which is combination means series or parallel combination. But if you have a circuit which is having a combination of resistors, it can be a simple circuit, it can be a complicated circuit. What we see is, let us say for example, we have like different resistors. I mean, maybe we don't know, there can be a lot of resistors also. Whatever is the net current drawn from this cell by the entire combination of these resistors, if you can replace the effect, if you can replace the entire effect by one single resistance, so all these entire set of resistors, right, there may be some of them in series, some of them parallel, like that we have a combination. The entire effect of all the resistors, if it can be replaced by one resistance, means what, this resistance is going to draw the same current. So whatever the current that is drawn from the cell, right, previously, the single resistance is also going to draw the same current. If you can think about such a resistance, right, which is replacing, so effectively what we are doing, we are trying to replace the entire circuit by just one resistance that is connected to the same cell, and it is going to draw the same current. Such a resistance, right, is what we call as equivalent resistance. So what is the idea of equivalent resistance, guys? This is important. So we have the entire combination of resistors. If we can think about a resistor which will draw the same current, we replace the entire circuit by just one resistance, and this resistance must be drawing the same current. Such a resistance is what we will be calling as what, equivalent resistance. And the idea of equivalent resistance is important because each and every time, right, if we have like really complicated circuit, we can't be dealing with the entire circuit each and every time. So what we'll do is we'll try and look at just the equivalent resistance part, and this will give us a picture of how the entire circuit is going to behave. So we will see how we are going to find the equivalent resistance. This idea, right, we have studied already in the 10th standard also. How do you find the equivalent resistance of series combination of resistors and parallel combination of resistors? But anyway, we'll take a look at it. So how do we find the equivalent resistance of series combination? So if we have two resistors R1, R2, they are in series combination, what we said, both of them will be carrying the same current. Let us say this combination is connected across the cell. Okay, the cell voltage is what, V. What is the voltage of the cell? V is the voltage of the cell. Now what we see is if we want to replace these two resistors by just one, that is what we are calling as what, the equivalent resistor, R equivalent. So R equivalent is going to draw the same current. So if the current I is here, means R equivalent is also going to derive how much current from the cell, it is going to derive the same current I. Now if you look at it, the potential drop across the first resistor is what, let us call it as V1. V1 will be what, I into R1. Potential drop across second resistor is what, V2, which is equal to what, I into R2. Potential drop across this plus potential drop across this will be equal to what, if you add both of them, then it will be equal to what, the potential difference between the cell terminals, which is what, V, the cell potential. So what we have is I into R1 plus I into R2 is equal to what, V. And in case of the equivalent resistance, this one resistance is only there. What is the current I? Resistance value R equivalent. So I into R equivalent, right, that is the potential drop across the resistor, that is equal to what, V. Let's call it as equation 1, equation 2. When we equate the potential here and potential here, right? What we are going to get? I into R1 plus I into R2 is equal to what? I into R equivalent. So I will be cancelled on either side. What we have is R1 plus R2 is equal to what, guys? R equivalent. So this is important for us. So if you have series combination of resistors, right? How do we find the equivalent combination, guys? R equivalent will be equal to what? R1 plus R2. If we have 3 resistors in series, what will be the formula for R equivalent? R1 plus R2 plus R3. If you have 4 means plus R4. Like that it will go on. That is how we are going to find the equivalent resistance of the series combination. Clear, guys? So understand what is the relation between the individual resistors and equivalent resistor. Same current I is going to go through each of these resistors which are in series, as well as the equivalent of these series combination. So whatever the current that will go through each of, because series combination means what? All of them will carry same current. Whatever current that is going through series combination, right? The equivalent resistance also will carry the same current. Clear, guys? So this is what is the series combination of the resistors and the equivalent resistance value. Now let us go to the parallel combination of resistors and how do we find the equivalent resistance in the case of parallel combination. So as we can see here, the resistor 1 and resistor 2 are what? Parallel. So we say that we connect it across a cell, okay, and the current I is drawn from the cell of voltage V. So here if you think about what is the equivalent resistor, right? So the equivalent resistor will be just one single resistance which is going to draw the same current from the battery. So what we see is the potential drop across resistor 1 will be same as the potential drop across resistor 2, which is equal to what? The cell potential. Which means what? If you look at the V value will be equal to what? I1 R1. Same V will be equal to what? I2 R2 also. So from here, right, what is the I1 value? I1 will be equal to what? V by R1. From here, what is I2 value? V by R2. So current through the resistor 1 is equal to what? V by R1. Current through resistor 2 is what? V by R2. If you look at the equivalent resistance, the current through equivalent resistance is what? I. So what is the I value? I will be equal to what? V by R equivalent. And what we see is the current drawn from the cell or battery, rate is splitting into what? I1 and I2. Means the value of I will be equal to what? I1 plus I2. Means what we have? I is what? V by R equivalent is equal to V by R1 plus V by R2. Here also V will be common. We will cancel it off. So what we have finally is 1 by R equivalent is equal to what? 1 by R1 plus 1 by R2. This is just for what? The parallel combination of two resistors. If you have many resistors, means what will be the formula? 1 by R equivalent is equal to 1 by R1 plus 1 by R2 and so on like that. So whatever the number we have, we will be able to do it those many number of times and we will get what? Essentially we will be getting the equivalent resistance value. So this is how we will find the equivalent resistance of series and parallel combination. So series combination, what is the equivalent resistance value? R equivalent is equal to R1 plus R2 plus R3 and so on. Parallel combination, 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. And one more thing that we will anyway explore while we are doing the questions on this. If you have any number of resistors, right, you know how we can achieve maximum resistance value? We can achieve the maximum resistance value by keeping them in series. Why? Because what is the series combination equivalent resistance formula? R equivalent is equal to R1 plus R2 plus R3 and so on. Means we are simply adding them. So if you are having a set of resistors, you want to achieve the maximum resistance, right? How we can achieve the maximum resistance? By having them in series. And we have a set of resistors. We want to achieve the minimum resistance. The minimum resistance will be achieved when we arrange them in what? Parallel. So we'll see it, while we are doing the questions also. But this is what is the series combination and then parallel combination of resistors. Let's look at this question, guys. Let's see if we can get answers for this. Given n resistors, each having resistance value R. There are how many resistors? N number are there. How many are there, guys? N number of resistors are there. Each is having how much resistance? R. how will you combine them to get maximum and minimum effective resistance? So how we need to combine them to get what? The maximum effective resistance and then minimum effective resistance. That's one question. Second thing they are asking is, what is the ratio of the maximum resistance to minimum resistance value? Second thing they are asking is what is the ratio of the maximum resistance to minimum resistance value? Yes guys, let's see if you can get answers for this. So what is the question here? We have n number of identical resistors. Each is having how much resistance value R. So using that combination, right, we have to get what? The maximum resistance value and minimum resistance value. And already we have been talking about it. When are we going to get the maximum? We'll get the maximum when we have the series combination. When we will have the minimum? We will have the minimum when we have the parallel combination. So let us check it guys. What will be the series combination? So series combination, right, we have n number of them. How many are there? N number. If you keep them in series combination means what is the R equivalent value? R plus R plus R, like that. How many will come? N number. So totally what is the value guys? N into R will come. Okay. So first one is series, second one is what? Parallel, omega version. Correct. Okay. So if you want to have maximum means what guys? We will have them in what? Series. And how we can have minimum? When we have them arranged in parallel. In that case, this is what? Max. And minimum case, 1 by R equivalent is equal to what? 1 by R plus 1 by R, like that. How many are there? N number. So totally what is it guys? N by R will come. 1 by R plus 1 by R, like that. N number of times what? N by R. So if you reciprocate it means what is the answer? R equivalent, the minimum case, right, will be equal to what? R by N. So remember guys, this is a standard formula, also a standard result. If you have n number of resistors, we keep them in parallel. What is the equivalent resistance of that combination? It will be R by N. Now the other part of the question is what? What is the ratio of the maximum to minimum resistance? What is the answer guys? Tara. Okay, so a lot of us are able to get the answer. What is the ratio of the maximum to minimum? Means what? We have to find R equivalent maximum divided by R equivalent minimum. That ratio we have to find. Okay, so what is it guys? N R by N. Means what is the ratio guys? N square, not R square. It will be what guys? N square. Check it. The ratio will be what guys? N R divided by R by N, right? So R will be cancelled. The N will go to the numerator. What will be the answer guys? It will be what? N square. Clear? The ratio of the maximum to minimum resistance will be equal to what guys? N square it is going to come. Okay. So we'll go to the next part guys. Look at this question. This is the fourth question of today's session. What is it guys? Find equivalent resistance of this combination. So we have a combination of resistors. What do we need to find? We need to find the equivalent resistance of the entire combination. We have to find the equivalent resistance of this entire combination. Okay. Jiva. Look at the fourth question guys. Question number 4, we have to tell what is the equivalent resistance of this entire combination. We have a combination of resistors and we have to find what is the equivalent combination of the entire the system that is given here. So here before you fire the answers, right guys, look at this. The way we will see it is, think about just one segment here. So you are having how many resistors here? 4 resistors. This 1 and 1 are basically what you can see. Is there any link or joint between them? No. Means what? 1 and 1 are what? Series. And this 2 and 2 are what guys? Series. So just focus on one link of 4 resistors here. This 1 and 1 are what? Series. Means what? The equivalent of them will be what? 1 and 1 series means what guys? It will become what? 2 ohms. The 2 and 2 are in what? Series. Means the equivalent of them will become what? 4 ohms. Like this. The next part will be what? Same. 2 and 4. The next part also is what? 2 and 4. The next part is also what? 2 and 4, like this. So what we are seeing is we have just done one level of simplification. Okay, Prajwal, you are saying the answer is what? 16 by 3. Okay, let's look at this, guys. So what we have, one link of 4 resistors. You see this 1 and 1 are basically what? Series, means it will become 2, because series means what? R equivalent is equal to R1 plus R2. Here 2 and 2 are in series, means what? It becomes 4. Now you see the 2 and 4 are in parallel. The 2 and 4 in what, guys? Parallel. So I want to bring one formula to your notice. If you have 2 resistors in parallel, right, guys, what is the formula for the R equivalent? 1 by R equivalent is equal to 1 by R1 plus 1 by R2. This is the formula we had, correct? So now look at it, take an LCM. It will be what? R1 plus R2 by R1 R2. That is the 1 by R equivalent value. Means from here the R equivalent value will be equal to what? You know, R1 R2 by R1 plus R2. This is the formula we can remember, guys. This is the formula we can remember. What is the formula? If you have parallel combination of 2 resistors, right, what is the equivalent of these two? It will be what? R1 R2 by R1 plus R2. This is the standard formula we can remember. Okay, lot of us are able to get the answer, guys. What is the answer? You are saying 16 by 3. So look at it, R1 R2 by R1 plus R2 means what? I am just talking about this 2 and 4. So 2 and 4, they are in parallel, right? So means what? 2 into 4, 8, divide by what is it, guys? 2 plus 4, 6. So 8 by 6 means what, guys? 4 by 3. This 4 by 3 is what? For this 2 and 4 in parallel, means 4 by 3. Next part is also what? Another 4 by 3. Next part is also what, guys? Another 4 by 3. Next part is also what? Another 4 by 3. Now how many resistors are there? The final values 4 by 3, 4 by 3, 4 by 3, 4 by 3. They are basically what? Series. Means what is the R equivalent value, guys? 4 by 3 plus 4 by 3 plus 4 by 3 plus 4 by 3. Totally what is the answer, guys? 16 by 3. Check it. What must be the answer, guys? 16 by 3 ohms. Lot of us are able to get the answer. So this is what we will be calling as the circuit simplification. Like, you know, we will not have just one resistor, we will have a combination. We will see that, you know, one set will be either in series or parallel, like that. So we have to simplify them, and then finally we will arrive at the overall equivalent resistance value. This is what we call as circuit simplification or circuit deduction kind of problems. Circuit simplification or circuit deduction. Clear, guys? Jiva, okay, Hridya, Amoga version. Fine. So good number of us are able to get the answers anyway. What is the answer, guys? It will be what? 16 by 3 ohms. Okay. Let's see, guys, if we can answer this one. This is another interesting question. Look at the 5th question. Given resistances 1 ohm, 2 ohm, 3 ohm. What are the resistance we are having, guys? We are having a 1 ohm resistor. We are having a 2 ohm resistor. We are having a 3 ohm resistor. The question is, how will we combine these resistors? How we have to combine them so that we get equivalent resistance value of 11 by 3. We get equivalent resistance value of 11 by 5. We get equivalent resistance value of 6. And we get equivalent resistance value of 6 by 11. So using these values, right, we have to get what? 11 by 3. We have to get what? 11 by 5. And we have to get 6 and 6 by 11. So how many resistors are there with us, guys? We have how many resistors? 3 resistors. We are having how many? 3 resistors. Using these, we have to combine them in different manner. How we can combine them? So think about the possibilities, guys. What are the possibilities we can think of? So different possibilities we can think about. So one thing is, straight we can say, let us keep all the 3 in what? Series as it is. Here 1 ohm, here 2 ohm, here 3 ohm. When we keep them in series means what is the R equivalent value? R equivalent value will be equal to what? 1 plus 2 plus 3 means what? 6 ohms. I think we got this. Third one we are able to get it. If you keep them in series means what is the R equivalent value? 1 plus 2 plus 3, it will be equal to what? 6. We got the third one. Now the other possibility is what? We keep them in parallel. We can keep all the 3 in what? Parallel. Like we can have 1 ohm, 1 by 1 plus 1 by 2 plus 1 by 3. What is the LCM here? 2 into 3 will be 6, right? So 6 plus 3 plus 2. What is the final value? 11 by 6. So R equivalent will be equal to what? Reciprocal means 6 by 11. Check it. Do we have this as a requirement? Yes. So we are getting what? 3 we got, 4 we got. So we got the equivalent resistance of what? Yeah, Amoga version. Arvind, you are also able to give the answer. So series means what, guys? You will get 6. Parallel means what? You will get 6 by 11. So both are done. Third and fourth are done. Now we have to think about how do we get the first one 11 by 3 and how do we get the second one. We have to think on how do we get the first one and then second one. So first one is what, guys? 11 by 3. Second is what? 11 by 5. Check it, guys. So how do we get the first one and then second one? See, if you remember this and the only possibility is, look at this. No, we have to have one resistor like this and the other two must be in parallel. This is the only possibility. What is the possibility? One resistor might be like this, let's say R1. Other two must be what? In parallel like this. This is the possibility of arranging them, because we are already completed what? All three series is done, all three parallel is done. Now here we have to play around with the resistor values. Remember, what is the denominator here? 3. If you have two resistors, right, we have the R equivalent formula. What is the R equivalent formula? R1 R2 by R1 plus R2. We are requiring denominator 3 means, think about it. Where we will get R1 plus R2? 3, 1 and 2. So think about it, guys. If you have the 1 and 2 in parallel and that is in series with what? 3. So 1 and 2 parallel means what? What is going to happen? The equivalent of this is what? 1 into 2 by 1 plus 2 means what? 3. Means what? 2 by 3. The equivalent of these two is what? 2 by 3. 2 by 3 is in series with 3 means what? 2 by 3 plus 3, which is equal to what? It will be 11 by 3. Clear? So we are able to get the first one. So how do we get the first one, guys? We'll have 1 and 2 in parallel, that is in series with 3. Now look at the next one. We have denominator what? 5. So where do we get R1 plus R2? 5. Think about it. R1 plus R2 will be coming as 5 when you have 3 and 2. Now look at this. We have 1 ohm separate and the 3 ohms and 2 ohms. They will come like this. So here 3 ohms and 2 ohms, what is the equivalent? 2 into 3 by 2 plus 3 means what? 6 by 5. Okay, and the 6 by 5 is in series with 1 means what? 1 plus 6 by 5 will be equal to what? 11 by 5. So thereby we are getting what? 2. So we are getting the hint. We are getting the hint by using what, guys? What is the denominator? Okay, so this is about how do we make the combination, because we know what is the order. The order is what? 2 will be in parallel, one of them will be like kept in series. Now which of them will be in parallel to achieve this particular combination? Clear? So this is what we have in terms of the formation of the circuits to achieve some particular resistance value. Okay, this is the last question for this session, guys. This is the question that has come in, I think it's come in AIMS 2015 paper. It will be a very easy question, you know. So what is the question? We have to find the equivalent resistance between A and B. Guys, this is a very detailed idea, finding of the equivalent resistance, right? In fact, probably tomorrow's entire class, right, we'll be looking at different models of questions on finding of the equivalent resistance. Like in that we have different shortcuts and techniques. A lot of things will come in this. Okay, so look at this question, guys. We have to find the equivalent resistance between A and B. Sixth question. Let's see if we get any answers for this, guys. Amoga version. You've been giving a lot of answers correct. Let's see if you can give the correct answer for this also. Check it, guys. We are able to get the answer. So what do we need to find? What do we need to find, guys? We need to find the equivalent resistance between what? A and B. We have to find the equivalent resistance between A and B. So again, these kind of questions, right, we have to always go by what? The simplification approach. So if you see this R and R, both of them are in what? We don't see any junction between them. Means what? These two are basically in series. When these two are in series, what is the equivalent of both of them? 2R is going to come. So look at this. We are going to do it step by step. We have this resistance as it is, and here we have the point A. Here we have the point B, that is as it is. Then here we have one more resistance. Here we are having one resistance. Okay. Across this we have the resistance. Okay. So this is R, this is also R, this is also R. And these two are in series, means the equivalent of them is what? The equivalent of them means we can replace both of them by what? 2R. We can replace both of these by one single resistance. What is single resistance value? 2R. Okay. So if we replace them by a single resistance 2R, guys, now you see that the R and 2R basically are in what? This is a parallel combination. The R and 2R basically what, guys? They are in parallel combination. So parallel combination means what is the equivalent value? Equivalent resistance value is what, guys? R1 R2 by R1 plus R2. 2R into R by 2R plus R means what? This is what? 2R square by 3R. 1R is cancelled. What is it, guys? 2 by 3R. So the equivalent of both of them will be what? 2 by 3R. Now look at it. I will have this resistance as it is. Then there is the point A. Here there is a point B. Here I will have my resistance as it is R. This R and 2R is now replaced by what? It is now replaced by one single value. How much is it? The value is 2 by 3R. Now you see the 2 by 3R and this R, right? Both of them are in what? They are having no connection in between them, no junction. They both are in what? Series. Series means the equivalent value will be equal to what, guys? 2 by 3R plus R. It is going to be what? 2 by 3R plus R is going to be what? 2 by 3R plus R. It is going to be 5R by 3. It will be about 5R by 3. Okay. So now we have the B as it is. There is a resistor R. Then there is the 5R by 3 and R. They both are in what? Parallel. The 5R by 3 and R, they both are in what, guys? Parallel. Now we have to find what is the equivalent of both of them. What is the equivalent of both of them? Same formula, R1 R2 by R1 plus R2. So look at this, guys. R into 5R by 3 divided by R plus 5R by 3 means what? Totally it is what? 5R square by 3 divided by denominator it is what? 8R by 3. So 3 will be cancelled, 1R is cancelled. So what is the final answer, guys? 5R by 8. So the equivalent resistance between A and B will be equal to what, guys? 5R by 8. So check how many of us are able to get the answer, guys? The equivalent resistance value must be equal to what? 5R by 8. So this way, right, we will be able to deduce this circuit, or we will be able to simplify the circuit. So step by step we will see where we have the series combination, where we have the parallel combination, and then do it. Usually, right, it will be done from one typical corner. So one corner where we'll have the things in either two resistors will be in series like this. Right here what we are having, you know, in one side this R and this R in what? Series. From there we are starting. So the circuit deduction problems, right, guys, they'll always start like this. They'll be starting from one corner where we'll have. So clear, guys? What is the equivalent resistance between A and B? Between A and B, the equivalent resistance value will be what? It will be 5R by 8. So I'm not sure if we are able to get the answers for this or not, because I have not seen many people typing the answer for this. Okay, so check the answer, guys. What must be the answer? It will be what? 5R by 8. And even once you finish the session, right, what you can do is you can go back home today, and then probably, I mean, obviously you are at home only. So once we finish the session, you can work out some questions and get the answer. Okay, so Kavya, you got the answer. Fine. So you can work out some more questions on this finding of equivalent resistance just on the simple circuits. When I say simple circuits, right, what I'm talking about is the series or the parallel kind of arrangement circuits. Okay, so in the next class we'll anyway be seeing some more problems on the simple circuits, the series and parallel combination circuits, and from there we'll slowly get into the core simplification part. The core simplification part of circuits, right, will involve one of the major principles, which is called as the Kirchhoff's laws. Okay, so we'll see that, guys. Harsha, you got it. Okay, fine. So we'll see those things in the tomorrow session. But before you come for tomorrow session, right, you guys just practice some more questions on the circuit simplification. Okay, guys. So we'll see in tomorrow session then.